Right, welcome back. Now we're going to look at how to draw a structure or displayed formula if you are given a name of an organic compound. You find that with organic compounds, if I give you this molecular formula, for example, C6H12, I know this is hexane, but this hexane can be written in several ways, or can be these carbon atoms and hydrogen atoms might be configured in a completely different way to what we've been looking at in terms of a straight chain hexane hydrocarbon. I could have this written like that with 4 carbons, and I have CH3 here. Right, we know that we can have branches, or I can have a straight chain. There are many other ways of writing the same organic molecule if I've got a formula like that. So it's important for us to be able to know where everything is within a formula, because when we write names, we say exactly on what carbon and how long the chain is, the principal chain is, etc. when we write the name. So this time now we are going backwards. We are starting with the name and going back to make the formula. But there are a couple of things that I want us to talk about before we start writing formula. Carbon atoms on the end of the chain are always attached to 3 hydrogen atoms unless there is a multiple bond on one of the first carbons. So all carbon atoms at the end, for example, if I've got this carbon atom which is at the end, it has got how many hydrogen atoms? 1, 2, 3 hydrogen atoms. But on this carbon atom which is at the end, not necessarily at the end of the chain, like all end carbons within the structure will have 3 hydrogens unless there's a double bond or multiple bond at the end of that structure. I'm saying double bond because that's the one we study at this level. We don't look at triple bonds, but let's just call it a multiple bond to get you to understand this much easier. Right, so if we look at this one here, it's an end carbon and there's a double bond. As a result, we've got 2 hydrogen atoms there. If we look at this one here, there are no double bonds anywhere, and all carbon atoms that are at the end of the structure, they have 3 hydrogen atoms around them. That's what we mean by that. Right, the next point I want you to bear in mind as we work through this section is carbon in the middle. If there's a carbon atom or all carbon atoms in the middle of the chain, they are attached to 2 hydrogen atoms unless there is a multiple bond or side chain. What do we mean by that? If we look at something like this here, if a carbon is sitting in the middle of the chain, let's look for carbon atoms that are sitting in the middle of the chain. There is a carbon sitting in the middle of the chain, carbon sitting in the middle of the chain. All these here, they've got 2 hydrogen atoms, but we've got this carbon here. It's sitting in the middle of a chain, but it doesn't have 2 hydrogen atoms simply because it has got a side chain that's coming out of it. That side chain could be bromine, it could be chlorine, it could be anything that qualifies to be a side chain. So as a result, this carbon will only take 1 hydrogen atom. Okay. Or if there's a multiple bond, let's look what happens here. We've got a multiple bond here, and this carbon that's sitting in the middle of the chain, it doesn't have 2 hydrogen atoms. It has got only 1. They've got 1 hydrogen atom. Both carbons that are sharing this double bond, they've got 1 hydrogen atom because they are sitting in the middle of the chain and there's a double bond. So that's what we mean by if there's a multiple bond or a side chain, you're not going to get 2 hydrogen atoms sitting on a carbon that is in the middle of a chain. Right. Now we're going to go straight into a skill practice activity. We're going to draw a structural formula given a name. So this is the name we're given. We're given 2-methylpentane. We need to write this as a displayed formula showing where all the atoms that are in the molecule or in the compound and where they are found. So we start from this end here right? This suffix ane tells us that there is no double bond. No double bond, and pent tells us that there are 5 carbon atoms in the chain, and methyl, there is a methyl group which is sitting on carbon number 2 of that chain. That's what this name is telling us. So we read it backwards and figure out, you know, first of all, whether there's a double bond or whether there's a multiple bond, and how many carbon atoms there are, and then we look at the side chains, those side chains, on which carbon of this principal chain are they sitting on. So right straight away I'm going to have 5 carbon atoms, and on carbon number 2 I can pick any, either this one or that one. I've decided to pick this one. There is a methyl group. So what do I do with the rest of the structure? We know that the rest of the structure is completed by adding hydrogen atoms, and when you add hydrogen atoms, be careful and make sure that, you know, all your carbon atoms are fulfilling their bonding capacity, and you need to show all the atoms. Don't just, I know some books have got this could have been displayed as 1, 2, 3, 4 like that. So this is another way of displaying this, but for this course, when we are asking you for a structural formula, this is what we are asking for. This is a skeleton formula where we've got at this end there's a carbon 1, 2, 3, 4 carbon atoms. We don't even show the hydrogen atoms, and on the second carbon we put a carbon there, and I put a CH3. Okay, we don't even show the hydrogen atoms. We don't want this here. What you're supposed to do at this level is this. That's what you're supposed to show. Okay, let's take a look at the next one. It's 3-ethyl hexane. Let's work it out again from this end. ANE, no double bond. Hex means 6 carbon atoms, and ethyl group is sitting on the 3rd carbon of that chain. So I will have 1, 2, 3, 4, 5, 6. And on the 3rd carbon atom, I'm going to have an ethyl group. Eth means 2 carbon atoms, so I write the C2H5. Okay, the side chains, it's okay to group the atoms, to group them and write it as in a condensed form like this, or if you want you can expand it. It doesn't make an awful lot of a difference. And the rest of the bonding capacity for carbon is completed by adding hydrogen atoms. So I've got hydrogen, 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 hydrogen there, a hydrogen there, and a hydrogen here. Let's carry on adding the hydrogen. Okay, one thing you need to do when you write a formula like this, because sometimes the names can be written wrong, and when you check, you follow the procedure I'm giving you or the method I'm giving you and produce the name as it is presented to you, you might find that the name doesn't actually produce a right formula. So if I count 1, 2, 3, 4, 5, 6, so that's fine. I'm just checking to see if these 2 carbon atoms I'm adding as a branch will not result in this being a principal chain. So that's okay, it's not causing that problem, so this name was properly written. It's another way of checking whether a name of an organic compound was written properly or not. Let's do 2,2-dimethyl butane. Right, as we were doing all along, an alkane, no double bond, and 4 carbon atoms. We've got methyl groups. How many of them? We've got 2 methyl groups, and they are all sitting on the 2nd carbon of the butane. So we've got 1, 2, 3, 4 carbon atoms, and on carbon number 2 we've got 2 methyl groups. Okay, and the rest of this I complete that using by adding hydrogen atoms to complete the bonding capacity of carbon here. So I just have to add hydrogen atoms, and yep, I've completed everything. This is 2,2-dimethyl butane. Okay, let's take a look at the next one. I think I'm running out of space here. I just need to clear this. Let's take a look at the next one, which is 2,3-dimethyl butane. It's pretty much similar to the other one. All we've done is we've moved the other methyl group to the third carbon. We'll have to check if it works out, but I'm sure it should. From what I'm just checked for quick assessment here, it will work out fine. So I've got a no double bond, 4 carbon atoms in the chain. I've got a methyl group on carbon 3 and carbon 2 of the chain. So I just go ahead and I'll just go ahead and produce the principal chain. On carbon 2 I put a CH3, and then carbon this I put a CH3. Okay, and the rest I complete that with hydrogen atoms as per the requirement of SCASA. Your syllabus, they want you to do this. They are so picky when it comes to your WACE exam. Even though you're doing this in year 11, the best you can ever do in life is to develop the right habit instead of getting used to what it's not wrong, but they just don't want it. So I wouldn't want you to say I'm saying it's wrong. Now let's take a look at this one here. It's 2-bromo-3,3-dimethyl-pentane. So we start from this one again, going back. Pentane, ane, no double bond, 5 carbon atoms, and on that 5 carbon chain structure, on carbon 3 we've got 2 methyl groups, and then on carbon 2 we've got a bromo side chain. So I have to check that out, produce the principal chain, that's 5 carbon atoms, and on the third one I've got CH3 and CH3 there, like that. Then I go on the second carbon. I can either pick this one or that one. You pick whatever you want. I'll pick this one for a change. Yeah, and this is where I'm going to put the bromo functional side chain, and I will add the rest of the hydrogen atoms to complete the bonding capacity of carbon and make that a complete molecule. So which means we'll be counting from this end. This is 1, 2, 3. So fine, it works out fine. And even if we count whichever way, this will remain the longest chain. These methyl groups I've added there won't affect the overall structure. Now let's look at the next one. 4-chloro-2-methyl-4-butyl octane. Okay, I might need more space for this one, and let's take a look if it works out, because sometimes the name might be correct, but might be incorrect, but still we'll be able to produce reproduce this, and we'll check whether it works out fine. Octane, it's 8 carbon atoms which don't have a double bond, and on carbon number 4 there's a butyl group, and on carbon number 2 there's a methyl group, and there's a chloro on there. So I will have my 8 carbon atoms, 1, 2, 3, 4, 5, 6, 7, 8. Double check, 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. So on carbon number 4, which is this one here, I've got C4H9. Yeah, that's the butyl group that we have there. And on carbon number 2, I will have this is carbon number 3. Carbon number 2 is this one. That's the one I want. I've got, because I'm counting from this end, guys, going that way. So I've got a methyl group there. And on carbon number 4 again, I've got a chloro. Right. And the rest I complete by adding hydrogen atoms to fulfill the bonding capacity of the carbon atoms. Okay, now let's double check, because usually I get a bit concerned when I get a large side chain like this, because it might cause the change in what I would have identified as a principal chain. So if I start from this end and count 1, 2, 3, 4, plus 4, that's 8. So this could be the longest chain, it's fine. It doesn't affect this long chain that I have here, so I wouldn't worry about that. Let's try from the other end. 1, 2, 3, 4, 5 plus 4 carbon atoms. This chain here would be the longest chain. So this one was supposed to be a no-name. This person or whoever reproduced this name was supposed to name this as, we take this as our principal chain with 9 carbon atoms, right? Okay, and on carbon 1, 2, 3, 4, 5 we've got a chloro, and then this one here will become our butyl group, which is 1, 2, 3, 4. So it was supposed to be named as 5-chloro, this is the correct name, 5-chloro, 5-butyl nonane. This is the correct name for this compound. This was a wrong name. So this just goes to show, guys, the importance of getting the name right, because someone must be able to reproduce that molecule or that compound you have named and get exactly the right formula. And when they double check, they should be able to say, perfect, this doesn't actually violate any of the rules for naming hydrocarbons or organic compounds in general. So this is really important for you to be aware of. And also with organic compounds, especially if you are going to end up studying things like your pharmacology, biomedical sciences, etc., you deal a lot in biochemistry with these organic molecules, complex organic molecules, which if you move one group to a next carbon, or if one group was meant to be on carbon 1 and it ends up on carbon number 2, that will change completely the properties of the biomolecule, the biochemical molecule you are trying to produce, or the biochemical molecule you're studying. So it's important to get those numbers right. Okay, let's take a look at the last one for this video. We've got 1,2-dichloro-3-methyl-heptane. Heptane, it's 7 carbon atoms, so I've got 7 carbon atoms with no double bond because it ends with ANE. 1, 2, 3, 4, 5, 6, 7. So I've got 3 plus 4, 7 carbon atoms, and on carbon number 3 we've got a methyl group. Yeah, and on carbon number 1 we've got a chloro, and on carbon number 2 we've got another chloro. The rest of these we complete them using hydrogen atoms. Just gonna do this, H, complete the rest so that it is a complete structure. Okay, perfect. Okay, there's another missing hydrogen here. Everything else is fine. Yep, apart from that hydrogen. So if we double check again, we've got 1, 2, 3, 4, 5, 6. So this side chain is not affecting our principal chain. The principal chain still maintains regardless of this side chain being added at this position. Unlike with the previous one, when we added this side chain, it altered what was meant to be our principal chain. That brings us to the end of this session. I shall see you when you attempt the next sessions.